Okay, so for today's lecture, I kind of want to pick up in the same kind of trajectory where we have been going. So the first part of this course has really focused in on API programming. So we've learned, we revisited the object-oriented principles that Java provides for us and how that allows for us to have encapsulation in our code and modularity in our code. And then we continue to see how we can start producing code, designing code by contract, right? So that there's the idea of a client developer and a serving developer. And so these API documentations that we can produce with Java docs allows us to effectively, as the designer of an API, give the client the contract that kind of represents as the contract documentation. And since we don't necessarily build complete applications with the API portions we're building, JUnit testing allows us to go in and validate and verify that all of the methods and classes we're designing work the way we expect them to. And so here, I want to kind of focus in today on packages, which will give us another form of modularity and encapsulation, similar to what we have with classes, but that'll give us data encapsulation in terms of defining subsystems in our application or being able to contain multiple classes together. So today we're going to talk about packages, what they are, how we've already encountered them, and how we should use them moving forward to build better code bases. So in this lecture, we're going to cover the basics of packages in Java. We'll see how to create packages and access the types we place inside them. We'll also discuss naming conventions and how that relates to the underlying directory structure. And then finally, we'll compile and run our packaged Java classes. And so I think today's lecture will stick mostly to some slides. I might do some code overview, though, if we have any time remaining. So in Java, programmers can create several classes and interfaces, as we've done in the past on multiple occasions. But after creating these classes and interfaces, instead of just leaving them all in one directory, it's actually better if you could divide them into subgroups depending on what their relationship is. So the idea is that you have these classes and interfaces which might handle similar or the same task. And if they do, you put those in the same directory or folder. And that folder is what we refer to in Java as a package. And so then what that allows for is the package can act as a container for classes and interfaces, where a package represents a directory that contains all the related groups and classes of those interfaces or of those classes. Okay, so a quick overview of Java packages. In Java, we use packages to group related classes, interfaces, and subpackages. The main benefits of doing this are, first of all, it makes related types. And in terms of types here, that would be like your classes, your interfaces, your records, your enumerations, or any annotations. So anything that's related as a top level domain, a top level construct in Java, it makes it easier to find. Packages usually contain types that are logically related. So when we look at some of the built-in types, we can kind of see what is the relation between these different classes that makes sense to group them together. Another advantage of using packages is that it avoids naming conflicts. So a package will help us to uniquely identify a class. So say, for example, we have a class called application that's defined in two different code bases and two different systems. Well, by having that class file exists in two different packages, in one instance, it might be the edu.uno.csci2120 com.application. The other might be com.github.ted.application. And so if those two class files, despite having the same name, are in different packages, we can import them in our application. We can even import them if we want to in the same source code file. Another advantage of using packages is it allows us to control access. We can control the visibility and access to the types of who has access or who has visibility to what's inside of that package by combining packages and access modifiers. And then finally, packages can be considered as a form of data encapsulation, right? And that's one thing we strive to do in an object-oriented approach is as we solve a problem, we kind of build a box to hide the mechanisms of how that is solved. And we then produce a interface, an API, where some client to our application or our subsystem, in this instance, our packages are really just subsystems, they can access our subsystem via the collection of method calls. So why use packages? Again, modularity and encapsulation. A lot of what we're going to be focusing on this semester is going to be the solid principles, which is all about building a code base that is as reusable, as flexible, and as robust as possible. So much like last semester focused on the dry principles, this semester we're going to focus on ensuring that you feel comfortable with the solid principles. And so in the first part of this course, we're really going to be focusing on API programming. So that's programming for the sake of serving other developers so that they can build out their own applications. Because in industry, a large part of what you're going to be doing is just building parts of systems in and of itself. And then after we graduate from this, we'll move on to the next parts of this class where we'll look into building our own graphic user interface systems, and we'll look into different forms of IO and serialization and being able to actually import and export data. And then we'll look at some of the containers so that we can have more complex data structures. So by the time we're done, we should be able to build full Java applications in a very modern sensibility. That's the goal here. But moving back onto to our packages, why use packages? Well, it's because of the modularity and encapsulation they prefer, that they allow. So packages, you want to think of it this way. Packages are to classes. When I say classes, I mean classes and interfaces. But packages are to classes what classes are to methods. So think about how Java organizes your code base. You can't just write code in a Java file, right? Your code has to go into a method. Your methods have to be defined into classes, and your classes then get grouped into packages. So all Java applications exist in that hierarchy. So the package is the largest, most hierarchical entity that code exists in. But it's possible for packages to contain packages themselves. So you can have a package that contains sub-packages. We'll talk about when you might want to consider using sub-packages in a little bit on these slides. So your class files are always contained within a package. So whether you declare that your class files are in a package or not, they are. So if you don't explicitly name your package, then your class files are implicitly in an unnamed package. And so that's not the most ideal solution, right? It works, and that's probably what you've been doing up to this time, but it's better if we explicitly label those packages instead of just having Java implicitly just use the unnamed package. And let's see here. Again, why would we want to use these? Well, we use them by default anyway, but why would we want to explicitly use them? Well, we've already mentioned this, being able to group our classes, interfaces, and sub-packages in a related way to make them easier to find. We already mentioned this, avoiding the name conflicts. We already mentioned this, the relationship from classes to interfaces as it pertains to methods to classes. And here, this is the big point, though, is that it allows us to write clean and organized code, and it allows us to organize our subsystems of our application to maximize reusability, flexibility, and robustness. So all of these other ones have been mentioned. So let's just focus on these two here. There we go. Okay, so there are two types of Java packages. You have the predefined packages, which are our system packages of the Java API, and you have user-defined packages. So you've already encountered the predefined packages. You've probably used some of the system packages starting on the first day of class. So the system packages, let's go ahead and do that. Okay, so the system packages of Java. Let's see here. Let me move this down here. Okay, so there are built-in methods. So Java also provides inbuilt packages, which contains lots of classes and interfaces. These are the classes inside the packages that are already defined that we can use simply by importing the relevant package into our program. So Java has an extensive library of packages, and a programmer need not think about the logic on how to do any of the tasks that are inside the packages, right? That's the advantage of the data hiding and providing an API. For anything that there's a method available in Java, all we have to do is look at the API documentation. We don't have to worry about developing our own logic to solve that problem. That's what it means for Java to be an extensible language. And from the get-go, we've learned how to extend the language outside of what other people have built. We've been building our own things from the get-go. And so the goal is for us to start building our own packages that we can supply to extend the system for others. So some examples of the system packages of the Java API that we might have already seen. So you have the Java lang package. And so this was the language support. This is the language support classes that are contained inside this package. These are the classes that the Java compiler uses, and therefore they're automatically imported. They include classes for primitive types, for strings, for math functions, for threads and exceptions. So ultimately, everything that Java actually needs as a language is inside of this package. And for that reason, this is the only package that is implicitly imported into your code. Java wouldn't be able to operate without this package. And you have the java.util package, which you've used again, probably from the very first day or at least the first week of programming. So this is the language utility classes and holds all sorts of useful classes, such as the vector class, hash tables, random, numbers, date, a number of things. Again, you can always check the API documentation for a full listing of what's inside that package. You have java.io, which is the input-output support classes. And so they provide the facilities for input and output of data. You have Java AWT, which stands for Abstract Windowing Toolkit. And so that's the set of classes for implementing a graphical user interface. And they include classes for things like windows and buttons and lists and menus and so on like that. You have the java.net package. And so that would be classes for networking. They would include classes for communicating with local computers as well as with internet servers. You have the java.applet, which are classes for creating and implementing applets. But ultimately, you could see the way that packages are designed is there's a common theme behind each one of the ones we cited, where we can give kind of an elevator pitch. We can kind of describe in a single sentence what what classes that package has towards that goal. So what are applets? It sounds like mini apps. Well, that's a good question. So applets are something that are not in vogue anymore. So when the internet was still a burgeoning technology, there was two competing languages that were vying for the coding language of the internet. So you had Java, who was attacking this from a kind of server side angle, and then you had Mozilla, who had developed JavaScript, which was a proprietary in-browser front-end language. And so an applet was the ability for a Java application to run inside the browser. Now, because of all the potential security vulnerabilities that exist inside of browsers, third-party plugins aren't supported like they once were. And because of the advent of HTML5 and CSS3 and ECMA 15, so the newest versions of JavaScript, what JavaScript used to not be able to do that you used to be able to rely on applet to do is no longer the case. So applets are still a package that exists, but it's one that you probably won't need to encounter very often because there's much better ways to do the things that applets used to do, if that makes sense. And, you know, it might just be worth removing the older technologies. Okay. So continuing on the system packages of the Java API, so the JDK and other Java libraries also come with their own packages, as we just saw in the previous slides. We can import those pre-existing classes that we want to use in our project in the same manner. So for example, if we want to import the Java core list interface and the array list class, both of those are in the java.util package. We use the keyword import, and then we use effectively the package name and then the class name to import that class into our source code. So the package name effectively serves as the class path, or where inside the system can the JVM go seek out where the class definition is at. So in this instance here, we're importing the array list from java.util and the list interface from java.util. And then once we import that, we can then use those in our application simply by typing their name, because then they're available inside the namespace of our application. So if I went ahead and I had imported list, here is the ability for me to declare a list variable. And if I had imported array list, here's my ability to go ahead and utilize the array list constructor. So again, nothing new here, but just highlighting that all of these imports we've been doing is adopted using packages. It's facilitated using packages. So that's just a quick look at the system packages, the built-in packages, the predefined packages that we've used many times before. But now what we should start striving to do, what we should start adopting, if we really want to elevate and skill ourselves up to be a little bit more professional in our practices, we should start striving to use user-defined packages in our own code bases. So users of Java language can also create their own packages. They're called user-defined packages, clearly. User-defined packages can also be imported into other classes and used exactly in the same way as the built-in packages. So all we need to do is put our related classes into a package. After that, we can simply write an import class from existing packages and use it in our program. A package is a container of a group of related classes where some of the classes are accessible or exposed and others are kept for internal purposes. So just like what we do with classes, the same concept. Some of our methods are public, some of them might be private that are the helper methods. Well, in packages, you have the same concept. You have some of your classes that are public and exposed to external code, where some of them are internal and designed for private consumption of the public ones. So you can think of them as helper classes. And then we can reuse our existing classes from the packages as many times as we need in our program. Let's see. So package names and directory structures are closely related to one another. For example, if a package name is edu.uno.cs, then there are three directories, edu, uno, and cs, such that cs is present in, well, this isn't quite right. CS is present in uno, and uno is present in edu. So you probably will notice that there's a convention here where, and this is a convention that Java had established, but it's not a steadfast one. It's one that you don't necessarily have to oblige by, but you typically use a domain name to represent your package. And so I'm using the standard convention here, but I do want to mention more about this when we get into the naming conventions. But effectively, whenever you have your package labels, and again, in Java, the dot operator represents that this thing is inside this other thing, right? In terms of scoping rules, so edu would be the root directory, uno would be a subdirectory to edu, and cs would be a subdirectory to uno. And inside of cs is where our class files would be. And so the path of the parent directory of, let's see, let's call this CS. So there we go. Okay, so the path of the parent directory of CS is what we call the class path, right? Because that is the location of where the class files are at. And recall that initially, Java knows where its own class paths are at for its local installation, and it knows where your source code files are at from when you first invoke your the Java runtime environment to go ahead and execute your code. If there's any additional class paths that need to be attached, that need to be accessed for your code to run, you have to stipulate that. And you can stipulate that in one of two ways. If you're at the terminal, you can tell Java to, I think the flag is CP, -CP will allow you to provide a new class path where Java can go look for additional class files at, or if you're using something like an IDE, you can go ahead and tell it to import into the external libraries directory that's maintained for your project. But do know that these dependencies, this is what's called the dependency, and dependencies are a pretty big deal. Class dependencies are a pretty big deal in big, larger scale Java applications. And so there's tooling called dependency injection that actually helps manage that complexity. So anyway, going back to the topic at hand, the idea is to make sure that the classes are easy to locate. That's the idea behind packages, because probably what you've been doing up to this point is you've had the single directory and all of your class files are going to the single directory. But that's not a great way to organize your code base. It would be comparable to just having all your methods defined in a single class, or having all of your source code defined inside of a single method, for instance. Like, it's not a good way of breaking down the complexity of your application. Okay, so let's talk about creating a package. To create a package, we have to use the package statement by adding it as the very first line of code in a file. So let's place a type in a package named, and again, we're going to use this edu.uno.csci2120.packages. What that would look like in Java code is the very first line of code would be the package declaration, so that this class can then have membership of this package. And so we could have a package if it be a single directory, or we can have a package that's multiple directories. And again, just by convention, typically it follows the namings of a domain name because those are guaranteed to be unique. And I'll cover that again a little bit later when we get to the naming conventions. And then after you declare the package membership for this class, then you would do your implementations like normal. So whatever your access type is, and then whatever type of top level Java file this is. So this is a class file, and then a class name, and then whatever the body of the class is here. Okay, so it's highly recommended to place each type, and when I say type, I mean class or interface or enum or a record or annotation into a package. If we define types and don't place them in a package, they will go into the default or unnamed package. Using default packages comes with a few disadvantages. The first is we lose the benefits of having a package structure, and we can't have subpackages. We can't import the types in the default package from other packages, and the protected and package private access scopes would be meaningless. So by default, you have, all of our source code is package private, but if you're not having packages, all your classes can just see all other classes, and that kind of starts to break the modularity of your code base. So as the Java language specification states, unnamed packages are provided by the Java SE platform principally for convenience when developing small or temporary applications or when just beginning development. Okay, in order to avoid packages with the same name, we follow some naming conventions, and this is what we've been seeing before. So it would be perfectly acceptable to have a package that's just called model, or one that's called view, or one that's called controller. In fact, in small scale projects, that's exactly how they're named, and there's nothing wrong with naming your packages that. Now, the reason why it's so common that you see these domain names used as package definitions, even to the point where in the first several of the directories, so like the edu and the UNO directories, there might not be anything else except for the CS directory inside there. But the idea is that the idea there is for uniqueness. So a domain name is unique. There was only one domain name. So if it's a organization or company or even an individual, if they're making public to the greater community of Java developers their source code so that they can import it as client code into their own applications, then it's important that that package has a unique class path. This way, it's possible to have multiple classes that have the same name. You might have like 20 different classes that are defined in Java that all use the name scheduler or have the name, say, for instance, node. But as long as they're in their own unique package or their own unique class path, you can actually import all of them into one source code file if necessary and utilize them. And so that concept of being able to easily import classes from other developers, that extensibility of Java, is what really kind of motivated this idea of having packages represent unique. Okay, so some basic convention stuff for naming your packages. So when we define our packages, use all lowercase. Package names are period delimited, right? So when we're looking at the hierarchical folder structure in the OS, we would use the slashes to say, this is the root directory, and then this would be the subdirectory, and this would be the subdirectory, and then all of the .java files go into there. But from the perspective of the JVM, from the perspective of Java, we would have membership to our packages. We would define our class paths by delimiting them with periods in between. And then names are also determined by company or organization that creates them. So for instance, to determine the package name based on an organization, we'll typically start by reversing the company's URL, because the URL again represents something that is unique. And then after that, the naming convention is defined by the company and may include division names and project names. Now, this isn't just something that is solely for professional developers, though. Even you personally have a URL that represents where all of your code lives at. And that would be either your GitLab or your GitHub account. So like, for instance, if you wanted to create a package name, what would be apropos would be, let's suppose you have a GitHub account, it would be com.github. Whatever your username is, .username, and then finally whatever the project name is. And so what that would represent is two things. It would represent a unique class path that your Java files would exist in, so that there would never be any other conflict with any other Java code out there, even if they have the same names, because they would have unique class paths. But it also serves as a reminder to anyone who's a client of your code of where to go to be able to find who the maintainers and stakeholders are. So for instance, if there's an issue with the code, or if they have a question with the code, or if they want to get an updated version of the code, the class path, using the domain name, especially if something like a repo, illustrates where you can go to find the source code files. Okay, let's see. Where did I leave off here? Okay, so let's see. So, and so for example, to make a package out of UNO's URL, www.uno.edu, you just reverse it, edu.uno. And then we can then further define subpackages of that, like edu.uno.csci2120, or even edu.uno.csci2120.domain. And effectively, all those are just subdirectories inside those directories. That's all that's being modeled there. Okay, so creating a package in terms of the directory structure. So packages in Java correspond with the directory structure, as we mentioned previously. So each package and subpackage has its own directory. So for the package edu.uno.csci2120, we should have a directory structure of edu, and inside of edu would be a uno folder, and inside the uno folder would be a CSCI2120 folder. So most IDEs will help with creating this directory structure based on our package names, so we don't have to create these by hand. And so again, if you're using IntelliJ, making packages and compiling packages is super, it's super simple. Okay, let's talk about how to use package members. So say, for instance, adding a class to a package. And I think we've kind of seen this already. So when we add a class to a package, we can add more classes to a created package by using package name at the top of the program and saving in the package directory. We need a new Java file to define a public class. Otherwise, we can add the new class to an existing .java file and recompile it. So I don't know if you know this, but it is possible to have multiple class files inside of one Java file, but preferably you should create a new Java file for each individual class. And then for each class, make sure that the very header of that defines what the package path is. Okay, let's talk a little bit more about subpackages. So Java supports this concept of package hierarchy, and this is done by specifying multiple names in a package statement separated by dots. So here's an example that we've been seeing all throughout our slideshow. So this approach allows us to group related classes into a package and their group related package into a larger package. So this allows us to store this package in a subdirectory that might be named, well, in this instance, the subdirectory would look exactly what you'd expect it to. So the root directory would be edu, then it has a subdirectory of UNO, and then that has a subdirectory of CSCI2120. But the idea behind subpackages is, again, this idea of kind of modularity and abstraction. So it's possible that, say, for instance, you're creating an item system, and an item system might be its own autonomous package, right? All the things inside of your item system might be interrelated in some fundamental way that's different than anything outside of your item system. So it would make sense to create a subsystem for some larger application that just imports the item, the item package. And so perhaps you have a larger package, a super package that's called inventory. And part of the inventory package, one of the sub packages that's part of the inventory package would be the items package. So you can already start to see, based off of just the homework that's assigned, how this concept of packages and then finding how packages themselves might relate into this broader sense can be defined into a larger scale package. And even if we look at the built-in packages, like all of the built-in packages are contained within the Java package. And then Java has multiple sub-packages, such as util, which represents utility classes, or lang, which represents the language-related classes, or IO, which represents the IO-related classes, that you would then naturally go look at for any one of those kind of specific tasks that you're looking to accomplish. You want to try to design your systems in a way that everything is easy to find in an intuitive way based off of the way that you kind of categorize and organize your source code files. So a Java file can have more than one class definition. Oh yeah, we already talked about this. But again, I prefer for your Java files to have the one class definition, but it is good for you to know that Java files can have multiple class definitions. Anyway, in such cases, if there are multiple class definitions, only one of the classes may be declared public. That's right. So the first one would be public, and all the other ones would effectively then inherit from that. And that class name with the .java extension is the source file name. And then when the source file with more than one class definition is compiled, Java will actually create a .class file for all the classes defined in there. So that's okay. So let's see here a little bit more about subpackages. Packages that are inside another package are the subpackages. Clearly, they are not. These are not imported by default. They have to be imported explicitly. Also, members of a subpackage have to access privileges, i.e., they are considered as different packages for protected and default access specifiers. So what does this mean that subpackages aren't imported by default? I'll give you an idea. So keep in mind that one of the way we use the import keyword to go ahead and import a package or a class or a collection of classes into our own namespace. So suppose I wanted to do java.util, or let's say, yeah, let's do util .star. So typically star would say, hey, take all the classes that are defined inside that package and import them into my source code file. Now, let's say that util has a subpackage and it's lowercase. Let's say, for argument's sake, without looking into it, there's this subpackage called exceptions. Well, because that's a subpackage, that doesn't get imported if I were to do .star. So what .star is going to do is it's only going to find the class files defined at that level. So if there's nested packages, it's going to ignore those for the purposes of importing classes into your namespace. So if you wanted to be able to import the classes from this subpackage to util of exceptions, you'd actually have to manually then do .exceptions. If you want to do all the exceptions, do the star there as well. So that's just what that means, is that when you import a package, especially if you're using the asterisk to go ahead and import all of the classes. It's just for the classes. It doesn't recursively then go into every sub package and import all of those. So keep that in mind if you want to access a sub packages classes, that you would have to do that explicitly. Okay, so an example of using the package members, let's start by defining a class to do item in a sub package named domain. So again, the way that this would look like in source code is I would have the first line of my code would be to declare the package. And then when I declare the package, I am going to declare all the way until effectively the directory that the class is going to be contained within. So if I want to think about this of how it would look inside of my computer in terms of the directory structure, it would be edu/uno/CSCI2120/ scheduler. And then inside of this directory would be a class, a Java file that's called to do item. So just like the Java files have to have the same name as the class name, the package name has to be the same as the directory structure. Java is very consistent in ensuring that what's being represented in source code is what's being represented outside of the source code in terms of the actual maintenance of all of your files and folders. Okay, so and then in this instance, then we can just create our class and whatever our class attributes are, just like normal. Okay, so let's talk about imports then. So I think we've already talked about this a little bit, but this will be a little bit more explicit and show you in explicit detail. So in order to use our to-do item class from a class in another package, we would then have to import it. So once it's imported, we can access it by name. We can import a single type from a package or use an asterisk to import all the types in a package. And again, we've probably seen both of these before, being able to import everything, the entire domain subpackage, or being able to grab the individual class. Now, typically, if you want to know what's preferred, unless you know you want to collect, unless you know you want to import multiple things, or if importing everything is not going to cause a conflict, typically it's safer to import just those classes that you want. And the potentially dangerous behavior you might get by just importing everything is that it's possible there is a class name that could conflict with a class name you're importing either from another external library or that you're using internally inside of your own source code. So for that reason, you kind of want to control what you import so that you always know what's inside of your namespace in terms of class definitions. Okay, so sometimes we may be using two classes with the same name from different packages. And one of the lovely things about packages is that's allowable. We can go ahead and have two classes of the same name. So for example, we might be using both java.sql.date and java.util.date. When we run into naming conflicts, we need to use what's called the fully qualified class name. So this is a fully qualified class name is the technical term of what we call a class along with its package hierarchy for any kind of class, for at least one of the classes. So let's use the to-do item with a fully qualified name so you could see what that would actually look like. So here, we can go ahead and inside of our list, when we're declaring the data type that can be held in this list, since there is more than one to-do item, here notice I have a to-do item, well, maybe if there's not more than one to-do item, I can still do this. This is still legal. This is the fully qualified name. So I can put to-do, which is located inside a scheduler, which is located inside of CSCI2120, which is located inside of edu, which is located inside of UNO, which is located inside of edu. By the way, like you could do this even with the other data types. So for instance, when you do string, you could actually declare string as java.lang.string, right? That would be representative of the fully qualified name for string. It's package and its class name. And so this is, again, useful if I had two different classes that I needed to use in the same source code file, but they're located in different places, or they have the same name. If they have the same name, normally that would create a conflict, but if I use the fully qualified class name, it would not. Okay, now in terms of compiling with javac, in terms of compiling in the IDE, in terms of compiling with IntelliJ, it's easy. You just go ahead and hit the compile button. You just hit the green arrow, and it manages how to compile all the packages together. Now, compiling from the terminal is a little bit more complex, and you should be slightly aware of how that works. So essentially, what's happening is when it's time to compile our package classes, we need to remember our directory structure. And then starting in the source folder, we need to tell javac where to find our files. Now, the nice thing about an IDE is the IDE tracks where all our files are located at, so that when the IDE tells javac to go ahead and compile your program, it already has that listing. But when we're operating at the terminal, we're the IDE, right? We have to keep in mind where all of the external class files are that we need to use that's not already part of the standard library of Java, or that's not already inside of our current directory. So in the example that we saw in these slides, we need to compile our to-do item class first, because our to-do list class depends on it. And again, we need to compile, since this list relies on instances of to-do item, I need to know where this is at and compile that. Now I can see it here, but I need to also give that class path to javac when I initially compile it, so I can go find the class definition and compile that and bundle it with your application. So to do that, you start by opening a command line or terminal like you would normally do, and navigate to your source directory where your Java file that you want to compile is. And then to compile it, it would look like something effectively like this. So this is one way of doing it. So javac, and then you would give the entire, so from the root directory, so from edu, you would then navigate towards where the actual Java file is in relation to the root directory. So edu represents our root directory. So to be able to tell javac where to-do item is, you're going to say, oh, it's going to be inside the subdirectory UNO, which is inside the subdirectory of CSCI2120, which is inside the subdirectory of scheduler, which is where the Java file is located at. And then if our class compiles cleanly, we'll see no error messages, and a file to-do item.class should appear in our directory inside of that subdirectory alongside where the .java file is at, just like normal. For types that reference types in other packages, so if we're trying to compile something, but we're importing from a different package, we might have to tell Java where that external class path is. So for those instances, we can use the -class path flag when we go to invoke the javac command, when we go to invoke the Java compiler, to tell javac where to find that compiled class at. So now that our to-do class is compiled, we can compile our to-do list and our to-do app classes. And so here, when we do javac, what we can do here is we can do -class path. We can put the class path that we want to go ahead and include. So in this instance, we're assuming that we're inside of the class path where to-do item is located at, but you can also make this a directory as well. So this, instead of just being a dot, could be something along the lines of like slash com slash GitHub slash TED slash scheduler slash, here's some Java files. And then here is the file path to the Java files that are currently being compiled by javac. And again, this approach for compiling, this idea of having to include the class path when you import these things, external user-defined class paths, is only relevant when you're doing this by yourself in the terminal. But it is something important to do, because one reason why you should be familiar, I'm going to give you a motivation why it's worth knowing this stuff, even though we're using IntelliJ to handle a lot of the management of our class paths in this class. It's often going to be the case in industry, or maybe even in your future coursework, where you're not capable of developing your source code on an IDE. And I'll give you an example. When you remote into a server, sometimes you can't have access to an IDE that you run locally. Often is the case when you remote into a server, to actually go ahead and implement server-side code, you'll SSH in through a terminal, right? Which gives you access to the machine, but that machine, especially with servers, they don't have a windowing head unit. They don't have a head installed on their OS because they're never attached to a monitor. So it doesn't make sense to have any graphics-based applications running on a server-based environment. So a lot of the times, the only way that you can interface with servers is from the terminal or the command line. So and a lot of times you have to deploy software in those server environments. So being comfortable, being able to navigate an OS and being able to code or execute your Java source code files from the terminal is an important skill set, because you're not always given the privilege to be able to use an IDE to create applications on your local machine. Sometimes you do have to remote in to be able to access and execute your files remotely. So that is a big point. And the other reason why it's worth noting is, if you know the commands on how to execute this, it's then possible to automate this as well. So if you ever want to create a script that launches a collection of services or Java services, then you'll easily be able to do that. And you won't have to necessarily rely on your ability to navigate the GUI, the graphics user interface, which is event-driven. You can't really program your application. You can't really script a set of events to navigate a GUI. It's just not worth it. I mean, I won't say it's not possible, but it's much more error prone than using a traditional, just command driven approach to telling a computer system on how to go ahead and execute scripts from the terminal. Okay, again, after we go ahead and execute this, though, we should see no error message, and we should find two class files that would now be in our well, not that package. Okay, so the last thing I'd like to say is when you go to run your application using the fully qualified name of our to-do app, it would look very similar to what you'd expect. You'd run Java from the root directory. And again, the reason why you're doing the root directory is you have all these subpackages where your source code files are at. So Java knows, starting from here, where everything else would be located at, because that's what you've been specifying. You've been specifying that the root directory for all packages starts at edu. So when you launch your source code, you want to be at the root directory. Again, since this has been the root directory, when you go to launch, you want to be at the root directory. But if your application with the main method is all the way here, you want to make sure to actually launch that as such. And actually, this should be slashes. There's not going to be dots on the terminal. There we go. And then that would actually launch, in this instance, a TUI, a command-driven interface on the terminal. So just a quick conclusion on packages. So in this short lecture on packages, we learned what a package is, why we should use them. We discussed naming conventions and how packages relate to the directory structure. We also saw how to create and use packages. Finally, we went over how to compile and run an application with packages using Javac and Java. And again, it's very simple to do in the IDE. And in fact, let me show you a repo that has a code base kind of separated. So here, let's take a look at this card deck repo. I'm going to, and clearly you can see this was produced in IntelliJ, right? There's the production folder from when it was compiled, and here's the source code file. So let me click in here. And so here's an example of how you might want to start thinking of how you might architect your applications moving forward, how you want to identify roles of related classes that will then go into a package. So for instance, in this card game, there are 1, 2, 3, 4, 5 different packages. There's a card game package. There's a controller package, a game package, a models package, and a view package. If I click in the card game, I will now have the Java files that relate to one another, that define what it means to be a card game. And if I click on card game here, you'll see it's got its package name. And then notice how it imports inside this application from the other packages. So look at how readable this makes the source code. So from the controller package, we're going to grab the game controller. From the game package, we're going to grab the high card game evaluator. And we'll also go ahead and import the from game the low card evaluator. Having issues with my UAs evaluator. Okay, let's see here. From our models, we're going to go ahead and import deck. From our view, we'll go ahead and import our command view. And we'll also go ahead and import our game swing. So here, inside of this class is our main method. So this is the launch point of this application. So all the necessary parts that have to get assembled together to make this game run are imported here. But notice it's done in a way that it's very intuitive on where you would go to find the various pieces that define this game. And let's just, without really caring about what this game does, let's see if we can't just read what this, parse what this main method's doing. So it's invoking this constructor game swing, which we imported from our view. So we're creating our game view, and then we're telling our game view, hey, create and show the GUI. And then the next thing we're doing is we're going to create this new high card game evaluator. And what is that? That's part of our game module. So we know, oh, we're creating part of a game. And what we have a comment here, highest card player winner. And here we're going to also create the low card game evaluator. And this is the lowest card player is the winner. Then we'll go ahead and create a new game controller, which is inside of our controllers. And we'll tell the game controller, hey, make a deck and then go ahead and run it. And so coming out of this, we can see what is a deck factory. Well, we can see what it imports. So our deck factory imports everything from models. And we can see, a deck factory is responsible for making decks. And we can tell, hey, what kind of deck we want to make. So when we say make a deck, we can give it a type, and it's either going to be a small deck, a normal deck, or a test deck. So this is what's using a factory pattern here. Okay, let's go back here to our source code. Let's see, just for argument's sake, what's inside of our game package. It's going to be all of the Java files that relate to the game logic. So the game evaluator, and if I click on game evaluator, I can see, oh, look at this. I have an interface on what defines an evaluator. And then Can we guess what high card game evaluator and low card game evaluator is going to be? They're going to be concrete classes that are then going to implement this interface. Perfect. So we can start to see here what good design looks like in a Java application. Again, jumping over here, we can see that the models, this is all the models used within the game. So a deck and a hand and the interface for a player, and then a normal deck and a playing card and a player, a concrete player, and then a rank, a suit. So these two things probably make a card, a small deck, a test deck. So these are the concrete things that we saw that could get made: a test deck, a small deck, and I think there was a normal deck. And then you have a winning player. And then and any one of these times I could inspect in and see exactly what's happening here. But yeah, so this is just to serve as a basic sample of what you should strive for, of identifying the related logics that classes combine themselves, and then you nest that into a package. And you don't necessarily have to have unique naming schemes as is shown here. Sometimes it's nice just to have something that, if it's a relatively small application, if you're not pulling from modules or packages that are coming all across the community, if this is all kind of internally composited by yourself, it makes for something that is easy to peruse and easy to identify when you're reading source code. Like when you're importing, here we're importing some built-in classes, and here we're importing a class from the controller. And obviously a controller are the things that the user uses to send input into the game. The views are the things that the model uses to display back out to the user. The models are all the internal things. And then finally, the game is actually the game logic, which is separate from the individual things that are being modeled that built into the game. Excellent. Does anyone have any questions on this sample, or does this sample help kind of have everyone understand how you should start breaking your code across packages now? Has this been helpful? Excellent. Well, we have about 10 minutes left, and I want to spend that time just covering something that you should have already covered, and I'm guessing you have, but I just want to ensure that everyone's on the same page. So I want to take the time to actually go over some naming conventions. And by naming conventions, I mean the actual Java naming conventions put forth by Oracle. So I want to ensure that everyone knows what the expected convention by other Java developers are going to have for everything you name inside of your source code files, because Oracle actually maintains documentation on how you should name your things. There's rules for that. And it's possible that you might have seen bad code or bad naming. And so if that's the case, I just want to cover this. So a quick overview for this, and this will be very quick slides because you've probably seen all of this already. We'll talk about what Java naming conventions are, and we'll talk about the conventions for packages, classes, interfaces, methods, constants, variables, and type parameters. And again, the rationale behind covering this is to ensure that you are primed for professional development. You should know all the rules as what industry would expect you to, like what other developers are going to expect from you. So let's go ahead and just burn through these. So here, Oracle has published the official Java naming conventions here. So I'll include this slide so you can have access to it. I'm not going to bother clicking the link because we already have most of these conventions named inside these slides. So you want to adopt the accepted convention for naming variables, methods, and objects in Java, because it makes your code easier for you to read, and it makes code easier for others to read. And when you start to understand what these conventions are, you're going to have an expectation for any Java code you look at, and it'll actually start to annoy you when people break those conventions. So this also, again, when we say others, this also includes you for when you read your legacy code weeks or months after, or maybe even years after you wrote it. Okay. Okay, so let's talk about for packages. You always use lowercase for packages. So never ever. So unlike with interfaces, unlike with classes where you use camel case, packages are in 100% lowercase. So package names should be unique. At least inside of your project, they should be like the one that we just saw. But ideally, they should be unique from every other package that exists, so that they're universally useful in any application without conflict. Use your internet domain reverse as a prefix for the package name. And even if you're not a company, you have an internet domain via your GitHub account or your GitLab account where you keep your repo. And then it's great because your package name is telling people where your source code files are actually repoed at. Oracle specifies the conventions for package names at here. So a web domain represents a unique organizational identity. It doesn't have to be a domain name, but for an organization, what uniquely identifies it is usually its domain name. So it's more like a convention than a requirement. That's the big thing. It's just a convention. But an example that you might want to use moving forward is something like com.github. And then whatever your username is, and then whatever the project name is after that. Or you could also use edu.uno.cscs.csci2120 if you want to for this class. But I would encourage you to use your GitHub domain because that would look more professional for when you use your code for repo purposes. It would make it look less like homework and more like code you've authored for the purposes of showing off. Okay, so some package naming conventions. We should really know all these because we already covered it. Why doesn't Java allow uppercase letters in a package name? Well, let's see here. This is valid, right? Everything is lowercase. This is what you might have been inclined to do if you use the same rules that you would have used for defining your class names or your interface names, right? The answer is that package names are written in all lowercase to avoid conflicts with names of classes or interfaces. So it's purposely in all lowercase so that the package name will never conflict with a class name. Okay, more naming conventions. The advantage of using the domain name convention, well, it avoids collisions between independent developers. A domain is unique. Two people can name two different projects the same, but a domain name has exactly only one owner. And it makes it easier to find the maintainer. If you inherit a code base that uses some open source library, it better be, you should find that package where it claims that domain name is at. Like that's the goal. That's the repo. That's where that package lives at. Other naming conventions. So non-domain name conventions, the general format for a namespace name is as follows. It could be whatever you want it to be, like the company, the product, the technology, and then you can use a dot and then whatever the feature is, and then you can use a dot and then whatever the sub namespace is. It doesn't even have to be a nested hierarchy like this as well. It could be like what we saw in that source code that I showed earlier, where it just separated in terms of roles, in terms of an MVC breakdown, a model view controller breakdown of what the application's responsibilities are. A very popular way to break an application down, by the way. So I'm just going to move on from here. Okay, so invalid domain name components that you should be aware of. So if you are using domain names, there are things that appear in URLs that you can't use inside of a Java path because it would be an illegal symbol. So for instance, the dash was an invalid symbol. You can't use it in variable names. You can't use it in class names. You can't use it in path names because when Java sees the dash, it thinks it's going to be for subtraction. So if you have a dash in a domain name and you're using the domain name as your package name, then you have to replace the dash with an underscore. Domain name components starting with a number should instead start with an underscore as well, right? Because that's anything that's invalid for naming variables or class names are also invalid for naming your package names. But again, if you're trying to model off of a domain name, you would then substitute a underscore as the first character because that is a valid character to start any variable name or class name, or in this case, package name with. And then domain name components that are Java keywords should have that component start with an underscore as well. So like, for instance, switch is a keyword in Java. So you can't actually use that as part of your package name because it's going to think that you're using the switch keyword. So what you'd have to use instead when you go to build your class path is the underscore. So when you reverse this, if this were the domain, it would become .github.underscore switch. Or if you wanted to have like 3D view as your package name, well, you can't start with a 3, right? You can't start with a number. So you can use an underscore if you needed to. And then let's say that this here was your URL, Ted-Holmberg. Well, again, this dash is invalid. So when you go to build this into the format of a package labeling, you'd replace the dash with an underscore. And so just some example package names. And again, we just went through an entire set of slides with this. So you should be comfortable with the naming notation on packages at this point. So for class names, you should always use camel case, and camel case where the first word, a letter of the class name is in uppercase, and each individual word thereafter is in uppercase. Class names should be nouns. So I don't know if they followed this in 1583, but there's actually rules on like how you should name things. So when you're defining a class, it should be a thing, right? Classes represent things. Things are represented as nouns. So obviously start with an uppercase letter, and each word in the name should also start with capital, hence camel case. So here are examples. I'm sure you've seen plenty of them, but just keep in mind, like this is by Oracle how all your class names should go. Uppercase starting with the first letter and each word thereafter. Don't use underscores, right? Don't use underscores for your class names. Interface names are capitalized like class names. In fact, everything that you would do for a class, you do with an interface, although usually by convention, this isn't a mandatory rule, but usually what you try to do with interfaces is it ascribes like a trait that something can have. So if it's possible to end with either IBLE or ABLE, that's what you do. So for instance, you'd have something that's comparable or serializable or editable or equipable, right? So these all represent, because an interface doesn't represent a thing in itself, right? It's this abstract thing that it's this abstract quality that other things can have. So you're trying to capture that sense that the interface is like a quality that other things can be a part of, that they can define, can be editable, right? Or flammable or breakable. But it doesn't always work. Like for instance, list, that doesn't make sense to have something that's listable. Well, I guess it does. I guess you could have something listable, but it's clearly you can see that that's not a steadfast rule. Okay, for method names, it should be the first letter is lowercase, and then you use camel case thereafter. Do not use underscores. You always use camel case if it's going to be more than one word. And for method names, unlike class names, you often try to use verbs, because remember, a method is supposed to be representing an action. It's trying to, or a behavior that's being performed by the thing. So like get name, add player, like these are like they're verbs or actions that are occurring. Size is breaking that rule. What would have been better is get size. But again, sometimes you'll have those outliers, but more often than not, you try to define your methods as an action or verb that your class does. Constants should be all uppercase. And so if it's more than one word, this is where you separate them with an underscore. And constants should always be declared as final to ensure that they can't be overridden. So again, examples of this would be like max int, where the max and the int are separated with an underscore, or severity added, or pi here. Your variable names should always use camel case. First letter is lowercase, and then each word thereafter is going to be uppercase. Your variable name should always be meaningful and indicative. And here, this is, I think I've seen some lab instructors violate this, and it drives me nuts. Do not use underscores in your variable names. That is a no-no in Java. Underscores are what are used in Python. It's called snake case, but we use camel case in Java. So again, and then for our type parameters, which you might not have seen yet, but you will see over the course of the semester, those will be single characters and they'll be capital letters. So, and typically the letter is actually indicative of what it represents. So when we get to generics, where generics actually have a type parameter, E usually represents an element, K usually represents a key, T usually represents type, V represents value. And then if you have secondary type parameters, so if you have more than one, then typically the follow-up ones you could use would be like S or U or other ones, any other one after that. Like V, you could use, well, if you go past a fourth one, I don't think that's very common. But yeah, so that's, I just wanted to ensure that everyone was on the same page after going through packages, that everyone's naming was also on point so that everyone is able to read and write and have an expectation of what Java code, how it's named and how it should look just stylistically. Excellent. So is there any questions that anyone has? So I would prefer, if possible, you experiment with packages on the current homework that we have. So like, for instance, as you're building out your item subsystem, it would be great that it actually exists inside of an item package. Because again, if you were developing this as at a professional level, that's what you'd want to do so that other client developers could import that package and then use it in their source code. And at this level of the semester, what I'm trying to get you used to doing is effectively be an API programmer, where you're building code that's really designed for someone else to use. And then we're going to pivot later on after we're done looking over some of these software design and development techniques to start building out our own applications. And I want to do some event-driven applications. I'd love to do some networking applications. I'd love to do some serialization applications that can read and write to files, or to even write in-memory data to the disk drive so that you can relaunch your software and restore a prior state to it. So these are all things we're going to be covering over the course of this semester. Excellent. Does anyone have any questions? If not, I will end our lecture for today. I'm sure that'll have to happen after class, though. Excellent. Well, I'm going to end this. If you have any questions that are related to problems, hit me up on Discord, and I'll try to help you from there.